Hello everyone, my name is Matthew KUNER and I'm a rising fourth-year undergraduate student studying material science at Georgia Tech. This summer, I'm participating in Texas A&M University's online O-REU program. The focus of my project is on developing a tool to automatically analyze shape memory alloy actuation fatigue data. Let's get started. Shape memory alloys, or SMAs, are a unique class of metals that can remember and return to their previous shape after being deformed. This ability to remember a previous shape is caused by a reversible phase transformation between the austenite and martensite phases. This can be induced by the application of heat and/or stress and results in what is called the shape memory effect, as shown in Figure 1. SMAs have seen application in the aerospace, biomedical, automotive, and oil industries. This project is primarily focused on actuation applications within the aerospace field, where SMAs can replace conventional actuators, such as hydraulic pistons, due to their lower density and relatively strong mechanical properties. An example of such an application is shown in Figure 2, where SMAs are used to change the geometry of an aero engine to significantly reduce noise upon takeoff or landing. One form of testing that SMAs undergo are actuation fatigue tests. Actuation fatigue tests involve placing an SMA sample under a constant load. Then, the sample is thermally cycled over a large range of temperatures, and the strain of the sample is measured. Idealized data from a single cycle of such a test is shown in Figure 3. Note that austenite is present at higher temperatures, whereas martensite is present at lower temperatures. The steeper regions imply that a phase transformation is actively occurring, whereas the flatter plateau regions imply that the transformation is complete. Key properties to measure from these tests are the start and finish points of these transformations, designated with the subscripts S and F, respectively. Referring to the figure, MS indicates the start of the transition from austenite into martensite. MF indicates that the sample is now fully in the martensite phase. AS indicates that the sample is beginning to transition back into austenite. Lastly, AF indicates the sample is now fully austenite once again. These four properties tell us what conditions are necessary for a material to be used as an actuator, and can also be used to calculate the total transformation strain as shown in the figure, which is essentially how far a material can extend and retract. Currently, transformation start and finish points are determined through the manual fitting of tangent lines to the data, as shown, and finding their intersection points. Even for a single cycle, this can be tedious. However, these tests typically last between about 500 and 30,000 cycles. Manually performing these calculations for that number of cycles is simply not practical. Hence, the aim of my project is to reduce analysis time to a matter of seconds, while also analyzing hundreds or thousands of additional cycles. Cycles were identified from raw data, with the cutoff between cycles being local temperature maxima. Cycles were then split into cooling and heating subcycles, shown in Figure 4a in blue and orange respectively. To find tangent lines for the steeper portions of a cycle, we first fit a logistic function, also known as a sigmoid, to each subcycle. Then, you find the lines tangent to these logistic functions at their steepest point. To find the tangent line for the plateau regions of a cycle, we use a different method. Starting from a small number of points, data at the start and end of each subcycle has a line fitted through it. Then, additional points are added, and a new line is fitted through the data. This occurs until the r-squared value of the fitted line dips below an arbitrary threshold, here chosen to be 0.9. Finally, we find the intersections of these tangent lines, which yield all four transformation start and finish points, as shown in Figure 4f. In Figure 5, you see all cycles for a real actuation fatigue test plotted together. Note that the average strain of each cycle is increasing, and that the shape of the cycles change. This video shows the tangent lines determined using my tool on real actuation fatigue data. As you can see, the tool is quite accurate in finding these critical points. While not shown here, similar results have been obtained from data collected by other researchers within the field of SMAs, implying a high degree of robustness. Here you can see the 4 calculated transformation temperatures over all cycles in an actuation fatigue test. The results are very accurate. We see that the transformation temperatures change significantly over the course of the fatigue test, some by more than 20 degrees Celsius. This evolution of transformation temperatures was previously difficult to quantify. Shown in Figure 8 is the evolution of the 4 start and finish transformation strains for the same actuation fatigue test. The results for strains are very stable as well. Figure 9 shows the evolution of the total transformation strain. Total transformation strain, shown in green, is calculated as the difference between the austenite start and austenite finish strains, which are shown in blue and yellow, respectively. Despite the fact that austenite start and finish strains both increase, the total transformation strain is quite stable. This means that the stroke length of the actuator, or its net change in shape over the course of a thermal cycle, is relatively constant. To make this tool usable for a variety of researchers, I've developed a graphical user interface, or GUI. Shown here is a demonstration of this GUI in action. First, the user simply selects a file for analysis. Next, they input what columns contain the relevant temperature and strain data in their file, facilitated by the preview table, which highlights the selected columns. The user can specify if they want to analyze all of the cycles in the file, or enter a custom range of cycles for analysis. Once the analysis is complete, files containing calculated material properties are exported alongside plots showing the evolution of these material properties. Let's sum up what we've talked about. I've created a robust method to automatically analyze shape memory alloy actuation fatigue data. This tool is able to calculate 19 different material parameters, many of which I didn't have time to talk about today, and is able to analyze data at a rate of about 30 cycles per second. I've also developed a GUI to allow other researchers to easily use this tool. Ongoing work includes further testing of this tool and increasing its efficiency. We also intend on pursuing publication of this tool in the future, as it has the promise to benefit many researchers within the field of SMAs. I would like to thank our sponsors, which include the NASA ULI program and the Summer 2020 online O-REU program at Texas A&M University. Finally, my work would not be possible without the support of the collaborators listed here. Thank you all for watching, and have a nice day.